Welcome to module number 6. This one's going to be a little bit different. We are covering the remainder of chapter 8, going over the proof of the soundness theorem. And then we'll also be moving on to a later chapter in the textbook that covers the completeness of propositional logic. And here by propositional logic, we just mean that we haven't quite introduced quantifiers yet. In chapter 9, next week, we'll introduce the notion of a quantifier. But this week, we won't have any main learning objectives. This video is just mainly focused on giving you the proofs of the soundness theorem and the completeness theorem of propositional logic, and then just sort of some of the consequences and making a few statements about what they mean. And really, the idea here is sort of that little subtitle down there. Really, it's the connection between syntax and semantics. On the side of semantics, we have whether or not our sentences or our propositions are actually true. And because we're dealing with sort of truth functional connectives, we've been using truth tables to produce those semantics. Remember, we also have some game semantics as well. And then on the syntax side, we've been dealing with forming sentences using our sort of recursive rules of conjunction and disjunction and negation, building up more complex sentences from our atomic sentences. And then likewise with proofs as well. Proofs are just sequences of sentences. And so they're really just a bunch of symbols and put together in sort of the right way. And there's not a whole lot of meaning involved in the sort of definitions for the syntax side of things, but instead just checking to see that things are well formed and that you've applied the rules, for example, correctly within a formal proof. And the soundness and completeness theorems give the connection between, or the bridge between, the syntax and the semantics. To make our discussions a little bit easier in terms of the syntax and the semantics, we're going to introduce two new symbols, and they're the turnstile symbols. The first is a turnstile with a single horizontal bar. That's in that first bullet point. And the second is the turnstile symbol with two horizontal bars, which looks almost like an equality sign with a vertical line sitting there on the left. And these will have some nice specific meaning, and it's just going to help us later on avoiding to write down sentences over and over again. We'll see this sort of information occurring so often that it's going to be helpful to just abbreviate it in this format. Now, the other thing that you're seeing there is a subscript of a T on those particular symbols. And that's because we can also define these symbols for other types of systems and other setups that we'll look at later on. But for now, you can think about the T as just standing for either truth table or tautological. So the first is just a shorthand way of writing down the fact that there is a proof from your premises to your conclusion. So here we'll write the sequence of premises, P1, P2, all the way to Pn. Then we put the turnstile with that single sort of horizontal bar there in the T. And then finally we write down that letter Q, provided that there is a formal proof of Q from those premises, P1 through Pn, using only the introduction and elimination rules for conjunction, disjunction, negation, contradiction, conditional, and biconditional. And those were our truth functional connectives. Recall that we also had a rule for equality introduction and equality elimination. And here that's specifically being left out because, again, equality is not sort of a truth functional connective, but instead a predicate that's interpreted the same way in all possible situations. So when that T is included on that turnstile, it's sort of explicitly saying that we are not using this equality introduction or elimination inside of our formal proof. just those introduction elimination rules for our truth functional connectives. Okay, and again, the reason we're introducing this sort of symbol here is that we'll be talking a lot about when there are formal proofs from certain premises, and we don't have to want to write down this sort of sentence over and over again. Okay, so that single turnstile there tells you that there's a proof from those premises to that conclusion Q. And again, that's a syntactic statement, right? That there's an actual proof, just there exists a proof. Now, the second turnstile that we'd like to introduce uses double bars, and it's part of that second bullet point down there. And we use sort of the same notation. So we put P1 through Pn, then that turnstile with a double bar and that subscript of a T, and then finally a Q. If Q happens to be a tautological consequence of the premises P1 through Pn. And again, this is a semantic sort of statement here. This is about the actual truth table. And again, I'll remind you that tautological consequence meant that when you constructed the joint truth table for P1 through Pn and Q, and looked at any rows where P1 through Pn were all marked as T or true, then the Q had to also be marked as Q as well. In other words, there's not a row in the truth table that makes P1 through Pn true and Q false, right? There's no counterexamples. And when there's no counterexamples like that, we say that it's a tautological consequence. And here we'll be sort of saying this enough that we want to abbreviate it just with this double turnstile. And the content of the completeness and soundness theorems will just be that essentially these two symbols are two ways of saying the same thing, right? So in fact, by the end of the video, I hope to convince you that although the definitions here are different, they're sort of representing the same thing, right? Now, keep in mind, the first definition up there is using information about the syntax of the system, and the second bullet is using information about the semantics, or just the truth tables. So now that we've introduced these two turnstile symbols, let's go through a couple of sort of results that we'll need later on in our proofs. And the first one is basically what I'm referring to here as the transitivity of tautological consequence. And remember that double turnstile with a subscript of a T is intended to denote the notion of tautological consequence. And here, what I'm sort of pointing out is that you can string together a series of tautological consequences to produce a new tautological consequence. And in fact, when we are building our proofs, this is essentially what we're doing. So we'll need to come back and talk about this as we prove the soundness theorem, and we look at some various proofs and how they're related to this tautological consequence. Okay, so nonetheless, let's start up there in those sort of blue bullets. We've got an if statement. So we're making an assumption first that P1 through Pn, those are sort of maybe the premises of our argument, or some assumptions that are in force in our particular argument. And we're assuming that Q1 is a tautological consequence of those premises. In other words, anytime P1 through Pn is true in a truth table in that row, then Q1 had to be marked as true as well. And likewise, the same is true of Q2 and Q3 all the way up to Qm. And furthermore, let's assume now down in this sort of green area that those sentences that we inferred tautologically, or tautological consequences, Q1, Q2, all the way to Qm, those sentences tautologically imply or have a sentence R, which is a tautological consequence of that, right? So in some sense, in the truth table, we've reasoned to Q1 through Qm, and then now we see that if Q1 through Qm are marked as T, then R had to be marked as T as well. And the only way that that's possible is if R is really a tautological consequence of P1 through Pn. And there's a lot of ways to maybe prove this. We could prove it by a contradiction, but ideally it's really just a matter of thinking about what happens in the truth table, right? So if we know the P1 through Pn are all marked as T, and then that forces Q1 through Qm to be marked as T. And then we know that anytime Q1 through Qm are marked as T, R is marked as T. Well, then clearly R had to be marked as T in the end. And you'll notice that this is sort of a form of transitivity. And for the most part, it'll be sort of important as we're arguing about the soundness of our rules. In other words, that our rules that we've adopted for our deductive system are preserving sort of tautological consequence as we use them. And this will be an important feature of that. So now that we've said a bit about the transitivity of tautological consequence on the semantic side, let's say a little bit about what we'll need to know on the syntactic side in terms of formal proofs to get our proof of the completeness theorem to work out later. So the important fact here is highlighted in blue on the top, and it's an if and only if statement. So whatever's on the left side of that if and only if and the right side of that if and only if, they're true at the same time. So they essentially mean the same thing. On the right side of that if and only if, we see that the statement says that there's a proof of S from the premises P1 through Pn. And that subscript of a T on our turnstile just means that we didn't use equality elimination or equality introduction. Okay, so if there is a proof of S from P1 through Pn, that's only because, in other words, if and only if, there was really a proof of a contradiction from P1 through Pn with the extra assumption of the negation of S. And so these two statements are equivalent to one another, and I'll give the proof on our next slide. But before we do that, let's introduce a new concept related to sort of that left-hand side of the if and only if statement. So the definition is this: a collection of sentences is said to be formally consistent if there's no possible way to prove a contradiction from those sentences. And here, I haven't explicitly said it, but again, we're working with our Fitch system and we're not using, or we're not allowed to use equality introduction or equality elimination, but only the elimination and introduction rules for our truth functional connectives. Okay, so if you can't prove a contradiction from your sentences, we'll say that we're formally consistent. Now, this is interesting because that sentence on the top actually is saying that if you're not formally consistent, right? So if P1 through Pn, along with the negation of S, is not formally consistent, in other words, you can prove a contradiction, then there really is a proof of S from those premises P1 through Pn. And because this is an if and only if, these two statements are also false in all of the same possible circumstances. And that's essentially what you're seeing highlighted on the bottom in blue as well. It's just an equivalent formulation of the sentence on top using our new definition. So if P1 through Pn and the negation of S is formally consistent, in other words, we could never prove a contradiction, that's if and only if there's not an actual proof of S from the premises P1 through Pn. And again, this is really just rewriting that if and only if statement up on the top in its sort of negated form, right? So if and only if means they're true in the same circumstances, but they're also false in the same circumstances. And here, this is what it means for those two sentences to be false. Okay, so on our next slide, we'll talk about how we prove a statement along these lines. But again, we'll need this bit of information about our formal proofs and this notion of formal consistency later on when we talk about the proof of the completeness theorem for propositional logic. So let's give the proof of that if and only if statement from the previous slide. Now, the first thing to recognize is that the if part of the statement is essentially trivial. So what you're seeing here on the screen is information about the only if part. But let's just say in words a bit about why the if part of the statement is true as well. Now, in the if part, we would assume that we have a proof of S from our premises P1 through Pn. And then we can construct a new proof by adding in an additional premise, namely the negation of S. And we could apply just simply one rule, citing that new premise S, and then the proof that we just went to get S from premises P1 through Pn to then derive a contradiction. Right? In other words, if we can prove S and we assume the negation of S, well then contradiction introduction immediately gets us a contradiction. So the if part of this sort of statement is trivial and essentially easy to prove. Now, the only if part is a bit more subtle, and I've included here a nice diagram from the textbook. So when we're proving this only if part, we're going to first start by assuming that P1 through Pn and the negation of S as our premises produce a contradiction. In other words, in our sort of Fitch format, that P1 through Pn and the negation of S would be above the Fitch bar. And then eventually, after some number of steps, and it may be lots and lots of steps here, we come to the conclusion that we have a contradiction. And all we've used are our introduction and elimination rules for our various truth functional connectives. Okay, so if we have a situation like that and we know that it checks out, right, all the rules are correct and it's cited all the premises correctly, well, then we can convert that into just a proof of S from the premises P1 through Pn. And we could do it just basically with a simple subproof. The idea is that you remove the assumption negation of S from the premises of the original proof and turn it into a temporary assumption in a subproof. Okay, so let's follow that white arrow over. So we're going to introduce sort of a new proof. We would first write down those premises P1 through Pn on the top. And now we're no longer allowed to assume the negation of S. But remember that a subproof allows us to make some of these temporary assumptions. So the first thing we'll do is jump into this temporary assumption in a subproof where we assume the negation of S. Now, when we have this temporary assumption of negation of S, we can just apply the exact same rules that we did in the previous rule to then reason down to a contradiction. Now, the only difference now is that that contradiction is only within our subproof, and it's based off of this temporary assumption of the negation of S. But that's perfectly fine. All of the steps still check out because you can use the exact same sort of citations that you had previously. And in fact, if we were numbering the premises and the lines here, you could use the same numbering as well because this negation S will come in the same position as it did before. But you'll notice that because we put it into a subproof, we can now sort of apply a different rule. Remember that negation introduction says that if you can reason to a contradiction under a temporary assumption, you are free to then conclude its negation. So here we temporarily assumed the negation of S. We arrived at a contradiction. So by negation introduction, we can arrive at the negation of S. And then finally, we can do negation elimination, citing that negation S, and then getting S. And so you'll notice here that we took our proof of our contradiction and converted it now into a proof of S from the premises P1 through Pn. Now, they're not the same proof, but they essentially use the same set of justifications. And the idea is that you're moving that negation of S out of the premises as a sort of assumption of the proof to a temporary assumption of the proof. Okay, and then again, don't forget that the if part of this statement holds as well. It's even a bit more trivial than what we just said here. And then, as in the last side, the important piece here is these sentences in their negated form. In other words, P1 through Pn and the negation of S are formally consistent if and only if there is not an actual proof of S from those premises P1 through Pn. And we'll need that notion of when there doesn't exist a proof in the completeness theorem. Now, with this information about formal consistency out of the way, we're ready to state the soundness theorem for propositional logic and prove it. Now, the soundness theorem says the following. There is a proof of Q from the premises P1 through Pn only if Q is a tautological consequence of the premises P1 through Pn. So here for the soundness theorem, essentially what we'll be doing is assuming that we have a proof and showing that the conclusion of the proof has to be a tautological consequence. And again, these subscripts of a T here on these turnstiles just means that we're only allowed to use the elimination and introduction rules for our truth functional connectives and not the introduction and elimination rules for equality. So the method for proving the soundness theorem is via mathematical induction. And here we'll do mathematical induction on the number of inference rules that we apply in our formal proof. So let's just say a bit about the strategy that we're going to follow here in this proof before we carry out the steps. First, we're going to prove a strengthened statement. So something a little stronger than just the soundness theorem. But as a consequence of that statement, the soundness theorem will follow. What we'll prove is that every line of a formal proof is a tautological consequence of all of the assumptions in force at that line. Now, the assumptions in force at that line include any of the premises of the proof, but then also any of the assumptions that the line may be part of in some subproofs. Now, the soundness theorem is just saying that the conclusion of such a formal proof is a tautological consequence, but we'll show that, in fact, every step along the way happens to be a tautological consequence of the assumptions in force at that line. Now, again, the way that we'll do this is by the method of induction. And so we'll first talk about what's called the base case. And in the base case, we consider proofs that only use one inference rule. And we show that they satisfy this statement that every tautological consequence, that every line is a tautological consequence of all the assumptions in force at that line. And it'll be fairly straightforward because we just have to think about maybe one rule that we could apply and verify that indeed we end up with a tautological consequence. Okay, so those are proofs that have just one inference rule applied to them. What about proofs that have more than one inference rule? Well, we'll take care of those in the inductive step. Now, in the inductive step, we'll first assume that all formal proofs that apply n inference rules or less satisfy the statement above. In other words, that every line of their proof is a tautological consequence of the assumptions in force at that line. And then we'll use that assumption to show that formal proofs that apply n plus one inference rules, in other words, one more inference rule, still satisfy the same statement above. And then, like dominoes sort of following, this will show us that formal proofs of any length with any number of inference rules applied satisfy that statement that every line is a tautological consequence of the assumptions in force at that line. And that'll be the proof of the soundness theorem. And again, here we're working by mathematical induction, and the induction here is based on the number of inference rules that we're applying. So let's first argue the details of the base case. And again, in the base case, we're looking at proofs that simply apply one inference rule among the introduction and elimination rules for our truth functional connectives. Now, it turns out that if you think a little bit carefully about it, these proofs can actually start with any number of nested subproofs. So remember, the first line of your proof can actually be a subproof. And if it is a subproof, then you'll have to put some sort of temporary assumption there into the subproof. And then again, on the next line down, you could have started a subproof again and again and again and again. And so before you apply any rules at all, you can start as many subproofs as you'd like. So you may have some assumptions from your premises, And then you may also have some assumptions from any subproofs that you might have started. Now, when we apply our first rule, all of those assumptions are going to be in force at that point. Now, the second thing that you should sort of take note of is that any of the rules that are required to complete a subproof can't be used as our first inference rule. Because in order to complete a subproof, we have to apply some rule at some point and then sort of end the actual subproof. And if we haven't applied any rules, we can't end any of the subproofs, and so we can't cite any subproofs at that point. So in other words, the only rules that we'll have to consider in this base case are rules that don't require a subproof in their formation. And then finally, down there on the bottom, since this is the first inference rule, it will only cite the premises or those assumptions of the subproofs. In other words, again, those assumptions in the subproofs and the premises are the assumptions that are in force at this particular stage. And what we would like to do is to show that whatever rule we applied, the line that we obtain is a tautological consequence of these assumptions in the subproofs and the premises of the actual proof itself. And that's what we'll do in our next couple of slides. Let's now go one by one through each one of the first rules that we could have applied and show that tautological consequence is preserved. The first we'll look at is conjunction introduction. Here, I've highlighted in green the sentences that we would need to cite in order to apply conjunction introduction and obtain the sentence in blue down at the bottom. Now, if this was the first rule that we had applied, then those sentences in green would be either premises or temporary assumptions within some subproof, and therefore they would be assumptions that were in force at the line at the very bottom. In other words, we can assume that they would be true. Now, if they're all true, then P1 through Pn would be true. And for the truth table for conjunction, we would find that the conjunction of P1 through Pn would be true as well. In other words, that line at the bottom would have to also be true. What this means is that the line at the bottom is a tautological consequence of the assumptions and premises in force at that particular line. In other words, we've established the base case if this was the first rule that we applied. Now, we could also have applied conjunction elimination, in which case we would only cite one sentence, and that would be a conjunction, in this case P1 through Pn. And we know that if a conjunction is true, right, if we're assuming that it's true, then every single one of the conjuncts has to be true, including Pi. So if we had applied this particular rule, then that Pi would be a tautological consequence of the conjunction up there on the top. And we would again have the base case in this particular rule. Next, let's look at negation elimination and disjunction introduction. In the case of negation elimination, again, I've highlighted in green here the temporary assumptions from either subproofs or the premises. And in this case, it's the negation of P. And again, because it's just an assumption at this point, we're in the base case. It's the first possible rule that we used. We can assume that it's true. And just thinking about the truth table for negation, anytime that the negation of P is true, P will have to be as true as well. So then that line in blue at the bottom would be a tautological consequence of the assumptions in force at that line. Likewise, for disjunction introduction, you're only citing one sentence. In this case, it's a sentence of the form Pi. Again, it'll either be a temporary assumption in a subproof or one of the premises. And because of that, we can assume that it's true. And again, from the way that the truth table is constructed for disjunction, if that Pi is true, then the disjunction of P1 through Pn will also be true. It's enough for one of the disjuncts to be true. And therefore, that line in blue on the bottom will be a tautological consequence of the assumptions in force at that particular line. Now let's look at the introduction and elimination rules for contradiction. The first thing to note is that contradiction elimination is not going to be a rule that we could apply at this point. The reason why is that, again, we're in the first rule that we could have applied. And to apply contradiction elimination, you would have had to have arrived at a contradiction. Remember, anything above the first rule at this point is either going to be an assumption from a subproof or one of the premises of the proof, and it's not possible to take a contradiction as one of the assumptions or the premises of the proof, and therefore we wouldn't apply this particular rule on the first step. On the other hand, we could introduce a contradiction on the very first step. And what that would require is that we'd have two sentences, P and the negation of P, somewhere above the line where we are applying contradiction introduction. Now, again, because this is the first rule, that would mean those lines in green there would be either temporary assumptions of a subproof or premises, and we could assume that they were true. Now, if both P and the negation of P are true, then those set of assumptions are inconsistent. And when you have inconsistent assumptions that can never be true at the same time, anything is a valid conclusion, including the contradiction symbol. So in this case, this would be a tautological consequence of the assumptions in force at that particular line. Now, it's important to point out that essentially any time that we derive a contradiction in our proof using contradiction introduction, that the set of temporary assumptions in force at that particular line are inconsistent with one another. In other words, they can't all be true at the same time. Let's finish off the remaining three rules we could have used on our very first step of a formal proof. Now, the remaining rules all have subproofs that they need to cite, and so it wouldn't be possible to apply them on the very first step. Let's first focus on conditional elimination. Again, just like our previous examples, the line in blue is what we're trying to prove is a tautological consequence. And the lines in green are temporary assumptions from subproofs or premises. And we can assume that those are true. So we'll assume that the conditional P implies Q is true and that P is true. But if we consider the truth table for a moment, the only possibility is that Q had to be true as well. Because if P was true and Q was false, then the conditional would be false, just based on its truth functional table. And therefore, that Q on the bottom line is a tautological consequence of those two lines in green. Likewise, for biconditional elimination, the difference being in the truth table that we use for the biconditional. In that case, the biconditional is true only when P and Q have the same truth values. And so if those lines in green, which are temporary assumptions at the moment, in force at the line in blue, are actually true, well, then P is true, and the biconditional between P and Q is true, so we'll be able to conclude that Q would be true as well. That would be the only possibility. And therefore, that Q is a tautological consequence of the assumptions in force at that particular line. And then, likewise, the last rule we could apply is just reiteration. And in that case, P is among the temporary assumptions or the premises of the proof, and we just reiterate it on a line down below, and it's clearly a tautological consequence because it's just the same sentence. All of the remaining rules include some subproof that you have to sort of cite, so this completes the base case. And again, I'll just remind you that what we've shown is that if we've only applied one rule in our formal proof, then we can be sure that that line that we arrived at is a tautological consequence of all of the assumptions in play at that particular line, or in force at that particular line. And here, that's anything that's above that line because it's the first rule that we applied. When we move on to the inductive step, that will no longer be the case. And we'll also have to consider what happens in the case that we deal with subproofs. Now that we've finished off the base case, we're ready to move on to the inductive step. Now, let me just give you a reminder of what we need to assume in the inductive step, what we'll call the inductive assumption, and then what we're after proving, or the goal of this particular step. Now, I've highlighted the first sort of line there in green because it's sort of like our temporary assumption that we had in our base case proof. So it's something that we'll assume is already true. And what we'll assume is that every line of a formal proof that uses n or fewer inference rules is a tautological consequence of all the assumptions in force at that particular line. And again, what we showed in the base case is that that is true when n is equal to 1. So if we've only applied one rule, then each of those lines is a tautological consequence of the assumptions in force at that particular line. Now, the goal is to show that if we apply one more inference rule, in other words, we consider a proof with n plus 1 inference rules, then the very last line, the one where we applied that n plus first inference rule, still has the property that that last line is a tautological consequence of all the assumptions in force at that particular line. And it's sort of like dominoes falling over. So in the base case, we showed that when n was equal to 1, this was true. So proofs that applied one rule, it was true that this statement held. And then if we prove this inductive assumption, then we'll also know that proofs of length 2, if we apply one more rule, still have this property. And then at that point, when we know that the case when n equals 2 is true, we can apply this same argument again and determine that n equals 3 is true, and then n equals 4, and n equals 5, and so on and so forth. And for any value of n, any number of inference rules that we apply, those lines in the proof will be tautological consequences of the assumptions in force at that particular line. Now, here I'm sort of going to try and color code things in our next few arguments because we'll be visiting again some of our formal inference rules. And I'll highlight lines in green where we can sort of safely make the assumption that those lines are tautological consequences of the assumptions in force at that line. And then I'll try to highlight those lines in blue that we're trying to prove are tautological consequences. And again, we'll be able to assume that those ones in green are tautological consequences. And this is where we'll start using the transitivity of tautological consequence that we sort of had mentioned, I think maybe in the first or second slide of this video. The last rule that we can apply in a proof is essentially any of them. There are no rule restrictions like we had in the base case. But before we jump into analyzing them rule by rule, let's first talk about how we might use our inductive assumption. So if you're looking at the proof on the screen here, this is one that looks like the last rule was disjunction elimination. And we'll conclude some sentence, say S, on the very last line. Now, if we assume that this proof has n plus 1 steps in it, then if we delete that very last line with S in it, and this use of disjunction elimination, we obtain a proof that has n inference rules applied. Because again, the proof that we were looking at had n plus 1, so if we delete that 1, we get down to a proof with n inference rules that are applied. And so the remaining proof, every line on that proof by our inductive assumption, our inductive hypothesis, is a tautological consequence of any of the assumptions in force at that line. Now, we have to be a bit more careful about assumptions in force at a line because now we're dealing with subproofs, and those can be temporary assumptions. However, before we jump into talking about subproofs, let me just point out that all of the arguments that we used for the base case and any of the rules that didn't use any subproofs basically still hold here. The difference now is that instead of the sentences in green being assumptions or premises that we can assume are true, they're tautological consequences of any of the assumptions in force at that particular line. And again, by the transitivity of tautological consequence, like we talked about in the first couple of slides, each of the arguments that I made before will work in the exact same way. You just have to add that extra step about transitivity. So what we'll do in the next 3 slides are analyze the rules that have subproofs in them and talk about why we still preserve tautological consequence in those cases as well. Okay, so with that said, let's focus now on if the last rule was really this disjunction elimination. Again, if we deleted that last line, we'd end up with a proof with n inference rules being applied, and every line being a tautological consequence of the assumptions in force at that particular line. Now, what that means is that, first off, that disjunction on the very top is a tautological consequence of any of the assumptions in force at that particular line. And those are the same assumptions that are in force at the line at the very bottom, and the conclusion that we're making, which is that sentence S. Now, if P1 through Pn is actually true, right? If we assume that the assumptions and the premises are true, then this P1 through Pn, that disjunction, will actually be true. And the only way a disjunction would be true, if we look at the truth table, is if one of the disjuncts is true. So let's say it was maybe Pi. Now, this is really an argument by cases because it could have been P1, it could have been P2, it could have been all the way up to Pn. But let's just assume for the moment that it was one of these disjuncts, namely Pi. Now, you'll notice that in addition to that disjunct at the top, we also have a series of n subproofs, one starting with each of those disjuncts, P1, P2, all the way down to Pn. And in particular, there would be a subproof that started out with that disjunct we know is true now, the P sub I disjunct. And every line of that subproof would be a tautological consequence of the assumptions in force at that particular line. Now, when we started that particular subproof, we placed a Pi at the very top to indicate that it was a temporary assumption in that particular subproof. But because of what we know about the first line, that there is this Pi that's actually true, that temporary assumption can be made to be actually just true. And therefore, that S is not only a tautological consequence of the assumptions in play at that particular line, but we can sort of discharge that assumption of Pi because we know it's true based on the disjunction up at the top. Now, again, we don't know which I it really is. It could be I is equal to 1 all the way up to I is equal to n. But the fact that we have subproofs for each of those possible cases just tells us that we have to go down to that particular subproof and then identify S as this tautological consequence. Okay. And so what that means then is that that line down there in blue is a tautological consequence of the assumptions in force at that particular line. Now, one issue that may arise or that could happen is if the proof was formatted incorrectly. If it wasn't constructed inside like the Fitch program or maybe like written by hand, you might cite a sentence that's inside of one of these subproofs incorrectly from sort of the outside at that line in blue down there, for example. And in that case, you might end up with something that's not a tautological consequence. But remember, Fitch bars these sort of citations. And in fact, if you construct your proof in the program, the Fitch program itself, then there's not even a way that you could cite back into a subproof. And instead, it just lets you cite the entire subproof itself. And so if you do have a correctly formulated proof whose last rule is disjunction elimination, then that last line will be a tautological consequence of the assumptions in force at that particular line. But again, we had to do a little bit more of an intricate argument here because we had those subproofs. Let's focus on biconditional introduction and conditional introduction. And since conditional introduction is a bit simpler, let's look at that first. Now, those lines that are highlighted in green, any of them will be tautological consequences of the assumptions in force at those particular lines. Now, if we focus on the line there in green that has Q, we again know that it's a tautological consequence of the assumptions. Now, if we focus now on the line in blue, that conditional, P implies Q, the assumptions that are in force in that line are almost identical to the ones in force at that line for Q highlighted in green. The only difference is that because Q is in that subproof that started with P, P is an additional temporary assumption. Now, what that means is that if all of the temporary assumptions that are in force on the line highlighted in blue, and additionally we know that P is true, well, then Q would have to be true as well. In other words, there's no possible circumstance where P would be true and Q would be false. And that means that that conditional would have to be true, and therefore it's a tautological consequence of the assumptions in play at that line. And notice that it doesn't require us to assume that P is true. That's not one of the assumptions in force at that line. But our subproof above shows us that if P were true, then Q would have to be true as well. In other words, there's not a counterexample. Now, moving on to biconditional introduction, essentially the same argument holds. If P is true, then Q is true. And if Q is true, then P is true. So they're true in the exact same circumstances. And those sentences that have been highlighted in green, the reason we can be assured that those tautological consequences are true is from the inductive hypothesis. And then that sentence down there in blue, that biconditional, is true because P and Q will have the same truth values. If P is true, then Q will be true. And if P is false, then Q will be false, and vice versa. And again, that's just based off of those two subproofs that we had above. We're now in a position to finish off the proof of the soundness theorem, and we'll look at our last two rules, negation introduction and contradiction elimination. And the thing that they have in common is that a contradiction appears in both of these proofs. Now, in the base case, we didn't look at negation introduction because it included a subproof, so it couldn't be the very first inference rule we applied in a proof. And contradiction elimination, again, also couldn't have been the first rule we applied in the base case because we can't take a contradiction as a premise or an assumption of a subproof. But it's important to note that this conclusion here, the contradiction, is a bit different than some of the previous sort of sentences we've been looking at. I'll remind you that the contradiction is supposed to represent a sentence that is always false. And so if that sentence is a tautological consequence of the assumptions in force at that line, it means that there's no way to make those assumptions in force at that line all true at the same time. In other words, there's no row of the truth table that makes them all true at the same time. They're sort of inconsistent with one another. And if there's no way to make the premises true, then there's no way to make the premises true and the conclusion false, meaning that there's no counterexample. And so the contradiction will certainly be a tautological consequence of the assumptions in play at that particular line. But again, that indicates that those assumptions were contradictory. Now, when those assumptions are contradictory, any conclusion at all is a tautological consequence. And so, for example, in this application of contradiction elimination, when we conclude P, certainly P will be a tautological consequence, because notice that it's the same assumptions in play as the line that had the contradiction, and the premises and assumptions in play at that point are already inconsistent. Okay, so that means that this contradiction elimination still preserves that tautological consequence. Let's now focus a bit on negation introduction and what happens when we arrive at a contradiction within a subproof. So here, again, we'll have that sort of extra temporary assumption of P. So if we focus on that line on the bottom, highlighted in blue, that's the negation of P. The assumptions that are in force on that line are the same assumptions that are in force on the line for the contradiction, with the exception of the extra assumption that P is true. And again, that's being indicated by the first line of that subproof at the top. Now, what that means is that those assumptions that are in force for the line in blue are inconsistent with P. If we additionally assume P, we end up in a contradiction. So if all of those assumptions in force on that line in blue are true, then P had to be false. And if P is false, the negation of P is true. And therefore, that line at the end, the negation of P, is a tautological consequence of the assumptions in force at that particular line. And that completes the proof. And that is the last rule that we needed to argue. And that finishes off the inductive step. And again, what we've shown now is the soundness theorem. In other words, if we have a proof of some statement Q from some premises P1 through Pn that only uses the introduction and elimination rules for our truth functional connectives, then we can be assured that what we are arriving at is a tautological consequence. Let's now jump into the completeness theorem for propositional logic, which is essentially the converse of the soundness theorem. So the soundness theorem, I'll remind you, said that if there was a proof, then we had a tautological consequence. The completeness theorem says if we have something that is a tautological consequence, that's only because there was actually a proof of that particular fact. And that's what you're seeing sort of displayed here in the form of an if statement. And remember, the soundness theorem was the only if. One approach to proving this conditional statement would be to assume that you do have a tautological consequence. In other words, from the joint truth table, anywhere where those premises are marked T, the conclusion Q is marked as T. And then take that information and construct a proof from those premises P1 through Pn of that statement Q. However, that particular proof requires a lot of moving details and is fairly difficult to sort of carry out. Instead, we'll follow the strategy of the textbook and prove what I've highlighted down here in green. That's the statement that if there isn't a proof of Q from those premises P1 through Pn, then Q is not a tautological consequence of those premises. In other words, in that joint truth table for P1 through Pn and Q, there's a row where P1 through Pn are all marked with a T, and Q is marked with an F. And furthermore, that occurs anytime there's not a proof of Q from the premises P1 through Pn using our introduction and elimination rules for our truth functional connectives. The proof is carried out in sections 1 and 2 of chapter 17. And as you read those, I'll just point out that the proof I'll give sort of goes about the proof in a slightly different format and a different variation. So it'll be a good idea to read through the proof in the textbook as well, because it'll give you sort of a different way of seeing the same proof. Now, when you read that proof, you'll see the term WFF, or WIF. That stands for well-formed formula, and we'll introduce it in subsequent chapters after chapter 8. But for the meantime, you can just think about it as being a proposition or a complex sentence like we've been dealing with back in chapter 8 and earlier. Okay, so let's outline the strategy and what we're after one more time. We're going to start by assuming that there's no formal proof of Q from the premises P1 through Pn. And then our goal will be to show that that the joint truth table has a row, just one row, that marks Q with an F and all of the premises P1 through Pn with a T. And what that'll tell us is then that Q is not a tautological consequence of P1 through Pn. Now, from that assumption at the top and our initial sort of discussion about the notion of formally consistent, what we can assume is that P1 through Pn, along with the extra statement, the negation of Q, is formally consistent. In other words, we can never prove a contradiction from P1 through Pn and the negation of Q. And again, we proved that back in the first couple of slides when we introduced the two different turnstiles and the notion of formally consistent sentences. Our first step is to expand that formally consistent set consisting of P1 through Pn and the negation of Q to a larger set. And we'll do it by considering all of the atomic sentences of the first order language that we're using. So here, the first thing that we'll do is just list them off. And here, it doesn't matter what order we list them in, just that every atomic sentence appears somewhere in this list. So we'll call A1 the first one, A2 the second one, A3 the third one, A4 the fourth one, and so on and so forth. And so all of the atomic sentences will be put onto this list. And it's really going to be necessary for us to do this expansion and consider all these atomic sentences, because later on, when we're proving the key lemma, or considering the key lemma for this completeness theorem, we will have to consider proofs that include atomic sentences that maybe don't appear in P1 through Pn in the negation of Q. And that's because if you applied something maybe like disjunction introduction, you could introduce an atomic sentence that didn't appear in these assumptions P1 through Pn and the negation of Q. But nonetheless, in our key lemma, we would like to consider those kind of proofs, and we'll have to actually consider that kind of proof. So here, we'll first expand our formally consistent set to a bigger formally consistent set. Here, the set we're going to expand to will denote by T, and it's a script T, as you can see down there on the bottom. And we'll argue that because the set we started with, P1 through Pn and the negation of Q, is formally consistent, meaning we can't derive a contradiction, that this larger set, and you'll notice here it's going to end up being an infinite set, but this larger set is formally consistent as well. Okay, so how does it work? For each of the atomic sentences, and let's just call an arbitrary one AI, there are three possibilities. The first is that there's a proof from P1 through Pn and the negation of Q of that atomic sentence. The second case is that there's a proof of the negation of that atomic sentence from P1 through Pn and the negation of Q. And those are actually two disjoint cases. And the reason they're disjoint is that our premises here, P1 through Pn and the negation of Q, as we said before, are formally consistent. So there's no way we could have proved both AI and the negation of AI. So that's where this assumption that our P1 through Pn and the negation of Q is formally consistent is used, so that case 1 and case 2 are really sort of separate cases. And then the third possibility is that neither case 1 or case 2 holds, and that means that there's not a proof of the negation of AI, and there's not a proof of AI. And what we do is we expand our collection to a bigger one, let's call it T here, that includes our sentences P1 through Pn and the negation of Q, and then all of those atomic sentences from either case 1 or case 3. Now, the nice thing about doing that, just throwing in case 1 and case 3, is that if you have an atomic sentence AI that's not in T, then the only possibility is that it must have been in case 2, meaning that there's a proof of its negation from P1 through Pn and the negation of Q. And we'll need that sort of later on. And then the second sort of nice observation to make here is that this set T remains formally consistent. If there was some contradiction that you could derive from this collection, well, then you could have arrived at that same contradiction just from P1 through Pn and the negation of Q. And that's because you have these proofs of AI. Or if you don't have a proof of AI, then you certainly know there's at least not a proof of negation or of the actual atomic sentence itself. And that's enough to make sure that that set T remains formally consistent. Now, again, we have to sort of expand this way so that we can consider proofs that include more atomic sentences than what's considered in our premises. Now that we've expanded to T, we can show that it is what the textbook calls formally complete. And that's highlighted there in gray. And that's the statement that every sentence in our first order language, there's either a proof from T of that sentence P or a proof of its negation. Again, that collection T is now infinite, but whatever proof that we write down of P or the negation of P can only include finitely many premises from those assumptions. Now, the proof goes by way of induction, but this time the induction is on the number of connectives in the sentence P. So what we'll do is argue like we did before. First, the base case, when the sentence has no connectives at all. Now, sentences that don't have any connectives are called atomic sentences, and they just consist of a predicate evaluated at some terms. And by the way that we constructed that set T, we looked through all of the atomic sentences. And so either we'll have a proof of that atomic sentence, or we'll prove the negation of that atomic sentence, depending on whether or not that atomic sentence was in T or not in T. If it's in T, then we have a proof. And if it was not in T, remember that meant that it was in case 2, and therefore there was a proof of its negation from T. Okay, so we have the base case, and hopefully that gives you some insight into why we were constructing T the way we constructed it, right? I mean, we really sort of built it in such a way that the base case became sort of trivial. Now let's consider the inductive assumption or the inductive hypothesis, and that'll be that our statement up there, highlighted in gray, is true for sentences in our first order language that have n or fewer connectives in them. In other words, if you have n or fewer connectives, then there's either a proof of that sentence or a proof of its negation from this set of assumptions, T. And our goal will be to show that if P has one more connective, in other words, n plus 1 connectives, then there is either a proof of the sentence or a proof of its negation from this expanded set script T. And if we're able to do that, then we will have concluded that this set of sentences, script T, is formally complete. In other words, it proves every sentence or its negation. So on the next slide, we'll talk a little bit about how we go through the inductive hypothesis. And it's a nice key lemma, or it's called the key lemma in the textbook. In the textbook, this particular result is the content of the proof of lemma 5 in chapter 17, section 2. Now, here we'll cover the details of when the primary connective is disjunction, but remember, the primary connective could be any of the truth functional connectives. And in the homework this week, I'll ask you to go through and prove the other connectives. So lemma 5 and its proof would be a great place to get started because it also has some details of those types of proofs as well. Okay, so again, remember, we have the inductive hypothesis, which tells us that if we have a sentence with n or fewer connectives in it, then our result is holding. In other words, we can either produce a proof of the sentence P or its negation from our set of hypotheses here, that being that expanded set script T. Now, we're going to suppose, or we're going to start by assuming that we have a new sentence P and it has n plus 1 connectives. And so it will have a primary connective. And here we'll be looking at when that primary connective is disjunction. In other words, there are two simpler sentences, Q and R, such that P is the disjunction of Q and R. Now, the important piece here is that the sentences Q and R must have fewer than n or n connectives in them. And that's because we've already removed one of the connectives from P, and so there are only n left over. And they have to be split up among Q and R. And therefore, by our inductive hypothesis, there are three possible cases. First, our assumptions, script T, could prove the sentence Q. Second, it could be the case that script T proves the sentence R. And then if case 1 and case 2 both fail, meaning there's no proof of Q and there's no proof of R because they have n or fewer connectives in them, there will be a proof of their negations. So the third case is that from T, there's a proof of the negation of Q, and from T, there's a proof of the negation of R. Now we consider case by case. In case 1 and in case 2, we extend the proof by adding an additional line and using disjunction introduction. And we introduce the disjunction of Q and R, in other words, P. So by adding simply one step and citing that final line of the proof in both case 1 and 2, we end up with a proof of P. So we then have a proof from our assumptions, script T, of the sentence P. So that's what happens in case 1 and in case 2. Now in case 3, we get sort of the exact opposite. We'll prove the negation of our sentence P. Now what you can do is merge the two proofs together. So you'll have, again, a proof from your assumptions of the negation of Q and a proof to the negation of R. And you can then merge those two proofs together, putting the lines for the first proof and then the lines for the second proof afterward. and then apply conjunction introduction and introduce the conjunction of the negation of Q and the negation of R. And then you can go through and just like we've proved De Morgan's laws in the past, we can from there reason to the sentence, the negation of Q disjunction R. In other words, to the negation of P. So in that third case, we end up with the proof of the negation of P. And because those three cases included all the different possibilities via our inductive hypothesis, we have now established our goal, provided that the primary connective was disjunction. Remember, there are several other truth functional connectives that we have to check as well. But again, I'll leave those as part of the homework for this week. Now that we finished off our proof that script T is formally complete, we can move on to constructing the row of the truth table that will verify that our sentence Q is not a tautological consequence of our premises P1 through Pn. However, we have enough information with our expansion T to construct basically a truth table or a row of the truth table for any sentence P whatsoever. And then we'll be able to prove a nice claim about those sentences in that particular row of those truth tables. So here's how it's done. Mark a T under any atomic sentences in the sentence P that can be formally proved from T. So again, here we're constructing the truth table for P. Presumably it has some atomic sentences in it. And so the first thing that you would have to do is sort of list those on the left side of your truth table and then enter all the various truth combinations. There being 2 to the n different rows where n is the number of atomic sentences. But again, here we would focus on just one row. And it would be the row where we would place a T under any of those atomic sentences that can be proved from script T. And then we place an F under any atomic sentences in P such that the negation of the sentence can be formally proved from T or from script T. And this includes all of the atomic sentences because our set is formally complete. It proves every sentence or its negation. And then what you can go through is going through the truth table, you can figure out the truth value of that sentence P in that particular row. And when you do that, it turns out that the following claim is true for all sentences P. There will be a proof of that sentence P from these assumptions, that expanded set script T, if and only if that sentence P is marked with a T in this particular row of its truth table. And the proof here is, again, by induction on the number of connectives. For the base case, we consider the atomic sentences because those are the sentences that don't have any connectives at all. And certainly from the way that we filled out the table in that first step, we marked a T under any atomic sentences that could be proved and an F under any where the negation could be proved. We certainly have this if and only if, right? In other words, we can prove those atomic sentences if and only if they've been marked with a T. Okay, so the base case is true just sort of trivially by how we filled out that particular row. Now, to prove the to prove the full claim, we'll first assume this inductive hypothesis. We'll suppose that it's true for sentences with n or fewer connectives. And our goal will be to show that if P has n plus 1 connectives, then the result holds. In other words, there's a proof of P from script T if and only if P is marked with a T in this row of its truth table. And again, I'll give you the details of just one of the sort of primary connectives. And in the homework assignment this week, I'll ask you to go through the remaining connectives. Let's now talk about our second key lemma. And I'm going to mainly focus on when the primary connective is conjunction in our inductive step. Now, the key lemma is also going to include information about when the primary connective is any of the other truth functional connectives, but we'll talk a little bit more about that on the next slide. And the proofs for the other connectives will be left to you all to finish for the homework assignment this week. Okay, so let's start here with our sentence P. And again, let's assume that it has n plus 1 connectives, and that we're in this case where the primary connective was conjunction. That means that P would be the conjunction of two sentences R and S. And furthermore, let's assume that in this row of the truth table that we constructed in our previous slide, that P is marked with a T. Now, because of the definition, the truth functional definition of conjunction, what that means is that R must also be marked with a T in that particular row, and so must S. Now, notice that R and S, because we've removed that conjunction, are now sentences that have n or fewer truth functional connectives in them. And so by our inductive hypothesis, there must be a proof of that particular sentence from our premises P1 through Pn. And that again is the sort of red arrow here. So that first white arrow was just from the truth functional definition of conjunction, and the red arrow is following from the inductive hypothesis. And what we get out of the inductive hypothesis are two proofs. A proof of R from P1 through Pn, and a proof of S from Q1 through QK. And it turns out that we can merge those two proofs together. We can start a new proof, and that's what this blue line is moving to. We can start a new proof, and in this new proof, we'll first put the assumptions P1 through Pn, and then the assumptions Q1 through QK. We then follow the exact same steps as the first proof and arrive at R. And then after that, we run through the same steps from the second proof and arrive at S. And again, we can just apply the exact same rules, citing the sentences in the same way that we did in the previous two proofs. Now, on the final step, we can apply conjunction introduction and cite the two sentences R and S. And the conjunction of R and S is our sentence P. And what we see here is that we've produced a proof of the sentence P. And so if we follow that sort of green arrow over, we can write that in the turnstile notation as T, script T, turnstile P. In other words, there's a proof of P from those assumptions in script T. Now, we also have to go in the reverse direction as well. But again, I'll leave the sort of second key lemma here as a homework assignment for you all to work on. So here is the full key lemma number 2. And in the textbook, it's labeled lemma number 3 in chapter 17, section number 2. And on the previous slide, we were really looking at that first bullet. And we showed that if there was a proof of R and a proof of S from some assumptions in this set script T, then we could put those two together and produce a proof of the conjunction of R and S. And we didn't talk about the reverse of that. However, we would need both of those pieces, that if and only if, in order to prove the inductive step for the primary connective being conjunction. For the primary connective being disjunction, we would need the second bullet here in lemma number 3. For negation, we would need the third one. And then for the two conditionals, we would need the fourth and the fifth line in this particular lemma number 3. In the homework assignment, I'll ask you to prove the various pieces of this lemma that haven't been proven in the textbook and haven't been discussed here in the video. But you'll notice that among the assumptions of the lemma is the fact that the set T is formally consistent and formally complete. And this is why we took such sort of painstaking detail to talk about the notion of formally consistent, and then to prove by induction that our expanded set T was actually formally complete. Because this lemma 3 wouldn't hold without those two assumptions. Okay, but again, I'll be asking you to prove the details of this. And again, these details are exactly what you would need to get the inductive step of our previous claim to hold. And that puts us in a position to basically finish off the proof of the completeness theorem. Let's now finish off the proof. Notice that there are proofs, formal proofs, from script T of P1, P2, Pn, and the negation of Q. In fact, they're really simple proofs. All you have to do is take one step and use the reiteration, because they're all elements of that set script T. Now, from our previous claim, where we constructed our row of the truth table, in the joint truth table for P1 through Pn and the negation of Q, we would mark all of those sentences with a T. And again, that just follows from that claim that we proved via induction in our key lemma. Now, if negation of Q is marked with a T, by the definition of negation, that means that Q must have been marked with a T. In other words, in this particular line of the joint truth table, P1 through Pn is marked with a T, and Q is marked with an F. That is, Q is not a tautological consequence of the premises P1 through Pn. And that is exactly what we were after proving. So that finishes off the completeness theorem for propositional logic. So just a quick reminder here of what we proved. We showed the soundness and the completeness theorems for propositional logic. When we proved the soundness theorem, we did it via induction on the number of rules applied within our proof. And by the way, that was a different proof than the one that can be found in the textbook in chapter 8, where they give a proof by contradiction and they look for the first invalid step. Here, our proof is essentially equivalent to that one, but we have brought the induction to the front. We then proved the completeness theorem, which the textbook waits till chapter 17 to prove. And again, we proved it via induction, but this time the induction required a couple of sort of key lemmas, and those inductions were on the number of connectives within our sentences. So we saw some fairly nice, powerful proofs. Now, the completeness theorem isn't quite done yet, because you all will need to complete lemma 3 and lemma 5 for the homework, looking at the various other cases of our inductive proofs. But nonetheless, when you fill in those details, you'll have a complete proof of both the soundness and the completeness theorems for propositional logic. And again, they tie together the syntactic side, which is just proofs and the methods for constructing proofs, and the semantic side, which is how we give meaning to our sentences via truth tables, as whether or not we believe those sentences are true or false. And the soundness and completeness theorem together tell us that those two things are essentially identical. uh, there is a proof of Q from P1 through Pn that uses only the introduction and elimination rules for our truth functional connectives, if and only if Q is actually a tautological consequence of P1 through Pn. So this sort of ends the first part of the textbook. And in our next module, we'll start up the second part, which introduces true first order logic, where we start to look at quantifiers like the existential quantifier and the universal quantifier. We'll again prove the soundness and completeness theorem for this strengthened first order logic in the second half of the book as well.